the biggest AI bet in America is not a new model. It is a promise to secure $500 billion of physical infrastructure. Data centers, chips, power systems, and transmission lines. The project is Stargate, built primarily to serve OpenAI. And the headline is not money already spent. In January 2025, Stargate announced a 4-year investment target. It said $100 billion would begin deploying immediately. That was the first hard evidence. But an announced target is not the same as committed capital. Committed capital means legally binding equity, debt, or purchase obligations. Financing capacity means money partners may be able to raise. Money spent means cash already paid for land, steel, chips, and labor. Public disclosures still do not provide an audited Stargate total for cash spent to date. That gap changes the story. Because the real bet is whether future demand can convert plans into fully operating campuses. At launch, the initial equity funders were SoftBank, OpenAI, Oracle, and MGX. SoftBank carried financial responsibility, OpenAI carried operational responsibility. Masayoshi Son became chairman. ARM, Microsoft, Nvidia, Oracle, and OpenAI were named initial technology partners. But even that list needs a warning label. ARM later told investors it had no formal commitment that its technology would be used. Being named at a launch is not the same as receiving a purchase order. By September 2025, the partners reported nearly 7 gigawatts planned in more than $400 billion mapped across 3 years. Abilene is live in phases, while multiple sites are under development across Texas, New Mexico, Wisconsin, Michigan, and Ohio. In April 2026, OpenAI said secured United States capacity had passed 10 gigawatts, not that every campus was finished. Why does an AI laboratory need infrastructure on the scale of a utility? Because frontier models do not run on software alone. Training divides enormous calculations across thousands of accelerators that must work together in near-perfect synchronization. Those chips continuously exchange model parameters and data through high-speed networks engineered for extremely low delay. When one link fails or one machine stalls, expensive processors can sit idle while the wider training job waits. Then inference begins, serving trained models to consumers, developers, businesses, and governments at every hour of the day. That requires more GPUs, storage, networking, backup systems, cybersecurity, and teams keeping the cluster available. The racks produce intense heat, so liquid loops, heat exchangers, and cooling controls become part of the computing system. Substations, batteries, generators, and transmission connections must deliver power without interrupting jobs that can run for weeks. The model may be digital, but the ceiling on what it can do is increasingly set by physical machines. Stargate works because different companies control different pieces of that machine. OpenAI defines the workloads, reserves capacity, trains models, and tries to turn compute into products and revenue. Chipmakers supply accelerators, CPUs, memory interfaces, and networking components, while foundries and packaging plants turn designs into usable systems. Cloud providers integrate those systems, operate the software layer, and sell reliable access to enormous clusters. Data center developers secure land, permits, buildings, cooling equipment, fiber routes, and the crews needed to assemble everything. Energy companies provide generation, transmission, substations, storage, fuel, and the agreements that determine when a site can actually switch on. Investors and lenders fund construction years before the final customer revenue is certain. These roles overlap. Microsoft remains an OpenAI partner, Oracle builds capacity for OpenAI, CoreWeave supplies additional compute, and all compete somewhere in the same market. Control over compute therefore controls research speed, product availability, and which companies can attempt the most advanced models at all. That makes the bottleneck strategic, and they begin long before a GPU reaches a rack. Advanced accelerators depend on scarce leading-edge fabrication, high-bandwidth memory, sophisticated packaging, and long manufacturing commitments. OpenAI said more than 5 gigawatts of Stargate capacity under development with Oracle could eventually run over 2 million chips. Those chips are useless without transformers, switchgear, fiber, cooling equipment, and enough skilled electricians to install them. Electricity is often the hardest constraint because a data center building can rise faster than new generation and transmission can be approved and connected. Land must be large, politically acceptable, close to power and fiber, and suitable for construction at industrial speed. Water can also become a conflict, depending on the cooling design and local climate. Some Stargate sites use closed-loop systems intended to reduce ongoing water consumption, but that does not eliminate every local resource question. The scarce resource is no longer just silicon. It is coordinated access to chips, electrons, land, water, permits, equipment, and labor at the same time. Now consider the financial assumption hidden inside the headline. $500 billion over 4 years averages $125 billion of deployment per year, if the target is fully realized. Stargate does not need one company to write one check. Individual campuses can combine equity, cloud service contracts, equipment finance, real estate capital, project debt, and utility agreements. The Michigan Stargate campus, for example, disclosed equity from related Digital and Blackstone-affiliated funds, plus long-term debt anchored by PIMCO-managed accounts. SoftBank has said it wants to limit its own capital burden through external financing, and it warns that projects may not proceed as planned if financing is unavailable on acceptable terms. That is financing capacity, the ability to assemble money. It is not the same as cash already spent. To justify the full scale, the campuses must stay highly utilized for years while covering electricity, maintenance, staffing, interest, and rapid equipment depreciation. Here is an illustration, not a forecast. A 10% annual return on $500 billion would require $50 billion of annual operating profit. At a 20% operating margin, that implies roughly $250 billion of annual revenue. At 30%, about $167 billion. That revenue would have to come from a mix of training, cloud capacity, consumer subscriptions, enterprise software, developer usage, and government demand. The thesis is that cheaper intelligence creates more usage faster than efficiency reduces the compute required for each task. If utilization falls, the same infrastructure becomes a fixed-cost machine waiting for customers. This is not vaporware, but it is not a finished network either. Abilene is already training and serving frontier systems. In July 2026, Oracle said its New Mexico project had nearly 700 local workers on site and had funded most of a $50 million water infrastructure commitment. In Michigan, hundreds of tradespeople were building 3 large data center buildings, with the first nearing completion in June. Those are measurable signs of construction. They still do not prove that every announced site will open on schedule or reach full capacity. Overbuilding is the first risk. Companies can reserve the same future demand across multiple proposed campuses, leaving some projects underused. Obsolescence is the second. A new GPU generation can arrive before a campus finishes installing the previous one. Supply shortages can delay chips, memory, transformers, switchgear, and cooling hardware. Permitting, grid interconnection, community opposition, and construction errors can push revenue years beyond the original financing model. And demand can disappoint. AI may grow rapidly while customers resist prices high enough to support the most expensive capacity. Partnerships spread risk, but they also spread dependence. A financing delay, cloud dispute, chip shortage, or customer slowdown can move through the entire chain. The more companies rely on the same infrastructure, the more one bottleneck can become everyone's bottleneck. Governments see that dependence as an economic and national security issue, not merely a corporate investment decision. The United States AI Action Plan explicitly links leadership to chip factories, data centers, and new energy supply. Federal policy has moved to accelerate permitting, open selected public land, support power development, and promote American AI systems abroad. The logic is straightforward. Countries that control advanced chips, reliable energy, and frontier-scale clusters can train stronger models, protect sensitive workloads, and set technical standards. But public support does not erase private risk. Communities still ask who pays for grid upgrades, whether electricity prices rise, how water is protected, and what remains after construction crews leave. Companies still have to convert extraordinary capital spending into durable demand. That is why the $500 billion number should be understood as a direction of travel, not a receipt. Stargate is becoming less like one sealed project and more like a network of contracts, campuses, financiers, utilities, chip suppliers, and cloud operators organized around OpenAI's appetite for compute. If that appetite keeps expanding, these sites could become the industrial base of a new economy. If demand slows, technology changes faster than expected, or financing tightens, some of the same sites could become monuments to overconfidence. Subscribe to Critical Failure for more investigations into the infrastructure beneath the digital world. Will this investment become the foundation of a new technological economy, or one of the largest speculative infrastructure bets in history?